All right, so we're going to pick up with solving for the equilibrium constant, which is given the symbol K. In our previous lesson, we had looked at how to set up the law of mass action um, for an equilibrium reaction. The law of mass action is sort of like a formula that you can use to help you calculate K, the value for the equilibrium constant. Just to remind you, the way that we set up the law of mass action, you take the products, concentrations, and raise them to their respective coefficient power. So the concentration of C raised to the J power. And then you multiply that to the concentration of D, that's your other product here, raised to the K power, divided by the concentration of the reactants, concentration of A to the H times concentration of B to the I. Let me also remind you that when you're setting up your law of mass action, we do not include solids or liquids in our law of mass action, as they do not have concentrations. They're considered to be constant. So in the previous lesson, we had actually set up the law of mass action for both of the reactions we see here. Both of these were balanced equations. And if you notice in number 1, we did not include the carbon or the water because that's a solid and that's a liquid. So notice I put a 1 here. The coefficients for both of the products were 1s. So it's concentration of carbon monoxide to the first power times concentration of hydrogen to the first power. For the second example where we set up the law of mass action, the products were aqueous here. One of the reactants was aqueous, but the water was the pure liquid, so we do not include it in our law of mass action, just like we did not include the carbon or the water here. So once you've set up the law of mass action, we can then actually plug in data to it. As I said, you could use this as a formula, and you can solve for your equilibrium constant, which is what we're going to do in example 1, 2, and I've added a third example here, 3. So number 1 is the same equation, same equilibrium as what we have up here in the previous example, number 1. So we're going to be using this as our formula, if you will. I'm going to write that down again just so that I don't have to keep shifting back and forth. So we had concentration of carbon monoxide to the first power times concentration of hydrogen to the first power. And there was nothing in the denominator here. So let's plug in our values. It says for here, number 1, if the concentration of carbon monoxide is 2.0 molar and the concentration of hydrogen is 6.0 molar, wants us to calculate K. So all you're doing is plugging straight into this law of mass action, your values. So we're going to have K equals concentration of carbon monoxide was 2.0 molar to the first power. Concentration of hydrogen was 6.0 molar, and that's to the first power as well. So we just have 2 times 6. So that's going to give us for our equilibrium constant value 12. We need 2 sig figs here. Notice the units end up being molarity squared. So that will be your answer on the first example. For number 2, the law of mass action that we had determined in the previous video lesson was K is equal to the concentration of hydronium ion to the first power times concentration of the acetate ion to the first power divided by concentration of acetic acid. And that was also to the first power. So let's plug in our values that they've given us here and solve for K again. They gave us hydronium ion concentration was 5.0 molar. And for the acetate ion concentration, that was 2.0 molar to the first power. And then the concentration of the acetic acid was 10.0 molar. So we basically just do the math. 5 times 2 is 10. And that will be molarity squared. Need 2 sig figs there. And then we have 10 divided by 10. And that's molarity. All right, so this molarity cancels with one of these and leaves your final unit for K on this example, just molar. 10 divided by 10 gives you 1. We need 2 sig figs, so 1.0 molar would be your answer on K for example 2. All right, so I added a third example here simply because I wanted us to look at a situation where the coefficients were not all ones. Because when you set up your law of mass action, the coefficient comes from the balanced equation. That's what we raise our power to. So, law of mass action for number 3. Take a second, pause the video, and see if you can set up your law of mass action and solve, and then resume the video and see if you get what I get here. So, law of mass action for this one, these are all gases, which means I'm going to include everything. So, go to your product side. Concentration of ammonia, NH3, and this is a coefficient of 2, so I'm going to square that. And then go to my product side, they go on the bottom. Concentration of nitrogen to the first power times concentration of hydrogen, and that's to the third power. So now we're going to substitute in our values that I gave you. So I said in this problem that the ammonia is 8 molar. We know the concentration of ammonia is 8.0 molar, and that's squared. Concentration of nitrogen is 2 molar, 2.0 molar, and that's to the first power. And concentration of hydrogen was also 2.0 molar, but this has got to be cubed because of that coefficient. All right, so we're going to plug in these values in. We have 8 squared is going to give us 64. And that's molarity squared. And then we have 2.0 molar times 2 cubed, and we know 2 cubed is 8. And that's going to be cubed as well. Remember, you cube your unit as well. So we basically have 64 divided by 16. And that's going to give us the 2 sig figs 4.0 molar. Let's see, this molarity squared cancels with one of these and one of these here, which leaves you with molarity squared on bottom. So the unit on this is going to be 4.0 molarity to the negative 2 power if you bring that to the numerator, because the actual unit is 1 over molarity squared. Notice your unit that doesn't cancels in the denominator here. All right. So hopefully you got that. Moving on to the nuclear chemistry section, I do want to just talk for just a minute about our symbols we see. These are our emissions: alpha, beta, gamma. There's your neutron. This is the positron, which is basically the anti-electron. If you compare this to the beta particle, which is basically an electron, you see the only difference is the positive one for the positron versus the negative one charge for the beta particle. I've always thought the beta symbol looks like a negative IE when I was first learning that. That just always helped me remember his symbol. Finally, the proton symbol that we use in our nuclear equations is 1 over 1h. Remember, the top number is your mass number, the bottom number is your charge or your atomic number. I also want to remind you, because we've done the first 3 examples here in the previous lesson, that the parent nuclide is what we refer to the uranium-238 as. And then the substance that it transmutates to is called the daughter nuclide. In this case, it's the thorium-234. And then here we have an alpha emission, or call it an alpha decay. That's your alpha particle 4 over 2He. Remember, when you're balancing your nuclear equations, you're going to treat the yield sign as an equal sign. And also remember that these are very simple. The superscripts on the left have to equal the superscripts on the right. The subscripts on the left have to add up to the subscripts on the right. So in the examples we did in the previous lesson, we went through the first 3. Let's look at 4 and 5. Now notice this is our yield sign here, so we treat this as our equal sign. Now in this case, we're trying to figure out what is being captured here. So we got to figure out what goes on the reactant side. There's only one product, 195 over 78 PT. All right, so let's get our numbers in place. Let's get our superscripts. So 195 plus X